AI systems often begin as tools of convenience. Over time, they can become systems we struggle to function without. What starts as optional support can evolve into structural reliance. And once that reliance is embedded across workflows, reversing it becomes difficult. Not because the technology is malicious, but because the system around it has adapted. Convenience is powerful. When AI tools speed up document drafting, automate customer support, optimize logistics, or generate forecasts, organizations experience immediate benefits. Time is saved, costs are reduced, output increases. Adoption spreads naturally because the improvement is visible and measurable. At this stage, dependency feels unlikely. The tool seems replaceable. The shift happens gradually. As AI systems integrate into multiple layers of operation, other processes adjust around them. Teams redesign workflows assuming automated inputs. Training shifts towards system oversight rather than manual execution. Over time, manual pathways fade. The system is no longer an enhancement, it becomes infrastructure. Consider predictive supply chain systems. Forecasting models guide production volumes and inventory placement. As accuracy improves, companies reduce buffers and operate closer to predicted demand. This increases efficiency, but it also reduces slack. If the system fails, or if conditions change beyond the model's assumptions, the organization may lack the capacity to respond manually. The convenience of optimization becomes structural reliance. A similar pattern appears in software development. AI-assisted coding tools accelerate routine tasks. Developers integrate them into daily workflows. Code review processes adapt to AI-generated output. Over time, fewer developers practice writing certain foundational components from scratch. If the tools become unavailable or change significantly, productivity may drop, not because capability disappeared, but because habits and structures shifted. Reliance grows quietly. There is also a concentration dimension. Many AI services are provided by a small number of large platforms. Organizations build products and internal systems around these external models. Switching providers can require significant reconfiguration of infrastructure, retraining of staff, and redesign of processes. Convenience reduces short-term friction, but can increase long-term switching costs. Dependency is not always technical, it is institutional. A common counterargument is that dependency is manageable. Organizations can design redundancy, maintain fallback procedures, and diversify providers. They can treat AI systems as modular components rather than permanent foundations. This is true in principle, but redundancy has costs. Maintaining parallel systems can reduce efficiency. In competitive markets, firms may remove backup processes to remain lean. The more optimized the system becomes, the harder it is to justify maintaining alternatives. Efficiency can crowd out resilience. Another argument is that technological dependence has always existed. Modern economies rely on electricity, telecommunications, and cloud infrastructure. AI may simply become another layer of digital dependency. This comparison is reasonable. The difference is that AI systems often influence decision-making itself. They don't just provide energy or connectivity, they shape forecasts, rankings, and risk assessments. When dependence extends into judgment processes, unwinding it becomes more complex. There's also a cognitive effect. As automated systems provide consistent outputs, users may lose familiarity with the underlying processes. If a pricing model continuously adjusts offers, managers may stop analyzing demand patterns manually. If an AI system screens resumes, recruiters may spend less time evaluating applications independently. Skills shift toward monitoring rather than performing. Over time, institutional memory of manual alternatives can weaken. None of this implies that AI dependency is inherently harmful. Integrated systems can improve stability, reduce errors, and enhance coordination. Deep adoption often reflects real performance gains. The concern arises when reliance outpaces awareness. If organizations assume that systems will always function as expected, they may underinvest in adaptability. Recent disruptions in cloud services and digital platforms have shown how interconnected modern systems are. When a central service experiences an outage, dependent applications across industries can be affected simultaneously. AI services embedded in multiple workflows may amplify similar effects if they fail or change unexpectedly. The more invisible the infrastructure, the harder it is to anticipate its absence. Managing dependency requires deliberate design. Organizations can maintain transparency about how models operate, preserve some manual expertise, and periodically test fallback procedures. These steps may seem inefficient, but they can protect against over-reliance. The goal is not to avoid integration, it is to avoid blind integration. As AI continues to evolve, convenience will remain one of its strongest advantages. The faster systems become and the more seamless their outputs, the more natural it will feel to build around them. The key question is not whether dependence will emerge. It is whether institutions recognize when it does. Fragile dependencies rarely announce themselves. They form gradually, as processes tighten and alternatives fade. By the time reliance is obvious, reversal can be costly. Understanding this dynamic does not require rejecting automation. It requires balancing efficiency with resilience. Because in complex systems, strength is not only about performance under ideal conditions. It is also about the ability to function when those conditions change.